Hi, Chris. I think we need to wait for a few minutes for other people to come.
That's right.
You're talking, yeah, you're in Dubna right now, right?
I am, yeah.
Mhm.
Which reminds me, I should change my internet connection just a minute.
Okay, don't worry. I'm waiting.
Okay, can you see my notebook?
Yeah, I can see the screen you share.
Okay, good.
I saw that Andrei Losев is also in that institute in Shanghai.
Yes, he's already there, in fact.
Yeah, I know this. He was going to go to Hong Kong, but now I think, but he ended up in Shanghai. I don't know.
So he's an old friend and collaborator of Sen, who is the deputy director.
Oh, I see.
So I think it's a good place for him.
I actually had a joint project with him last year, but he was too busy to continue. So probably I'll try to resume it.
Well, you should come to Shanghai to visit.
Yeah. I'll take opportunity. Take the opportunity to take advantage of this. Let's see. Okay.
So I think already there's an active mathematical physics seminar there. Other than that, I'm not sure yet what else is going on. So when I go, I plan to start some kind of seminar in kind of derived algebraic geometry, some homotopy theory related to it.
But that's really interesting.
Здравствуйте.
Здравствуйте.
Крис, у меня лежит ваш конверт с договором. Мне его передали. Я не знаю, как теперь мне его вам отдать, но...
Ну, Крис вроде как...
Но мне кажется, это как не очень важно или срочно, потому что у меня есть электронная копия.
Ну, хорошо.
Ну, ничего.
Как мне передать его?
Ну, как-нибудь передадим. Вот. Вы будете...
Да, жаль, что я хотел прийти, очно читать доклад, но, к сожалению, поезд река едет, и было бы неудобно сегодня.
Ну, я понял, да.
Да, ну, Дубны далеко ехать, очень долго. Вообще...
можно было Коле Тюрину отдать, наверное. Он же периодически бывает.
Да, можно так, да.
Давай, на самом деле, передадим через Колю. Я просто...
Да, через Колю или через Ольгу Гришину.
Через
Колю проще. Ну, ладно. Еще я забыл в Пекине у вас взять этот QR-код от Вичата, потому что контакта так и нету. Если вы можете Гоше переслать.
Ну да, пожалуйста, да.
Да, и Бондал вам передал книжку?
Да.
Какую книжку, Саш?
Я постепенно читаю, да.
Я понял.
Все, ладно. Ну, просто она дошла, ладно. То, что я хотел узнать.
Гадость Бондал прямо, честно говоря, я Бондала видел только вот в прошлый вторник. когда все это...
Ну, я его вот периодически вижу, там он бывает в Стекловке, во-первых, и я иногда бываю. Во-вторых, я его где-то видел... ну, Гош, мы же с тобой его вместе видели.
Я и говорю, я только в прошлый вторник его видел, да.
А до этого я еще где-то... на юбилей Прохорова еще я его видел.
Мне кажется, Бондл сейчас не в Дубне. Просто. Крис же работает, вы работаете же в лаборатории Бондула.
Да.
Понятно. Окей. Ну что, Саш, подождем еще чуть-чуть. В принципе, я смотрю...
Пару минут можно, да. Так, в принципе, уже народ есть, но может еще кто-то захочет.
Я смотрю, все, кроме Джунху, говорят по-русски.
Ну да. Ну, я думаю, в любом случае Крису будет легче говорить на своем родном языке.
Да, это наверное.
Кстати, Крис, а вы...
Знаете, да, мне кажется, это будет легче вам. Потому что я все прекрасно понимаю, что я говорю, но другие не понимают, что я скажу.
Ну да.
Ясно. Да, и, Крис, извините, а вы вот в Сколково на прошлой неделе тоже об этом делали доклад, или там что-то другое было?
Где?
В Сколково.
Нет, это было другое. В прошлом году, что-то похоже было, но несколько недель назад я был там и читал другой доклад. Но в прошлом году я что-то пытался там читать, но там они как почти как физики.
Ну да.
Если ты скажешь что-то слишком абстрактно, это будет страшно.
Ну да.
Это вы у какого-то квантового центра, что ли, читали?
Не квантовый, это центр Кричевера.
Нет, Кричевера, они как раз вполне математики. Что-то странно, что вы это...
Нет, ну там действительно, Гош, разные люди есть. Там, конечно, есть математики, там типа Миши Финкельберга, но там есть и больше к физике люди, там, по-моему, Забродин, ну вот из ЭТМФ.
Забродин, Маршаков главный. И надо...
Да.
Маршаков. Ну да, Маршаков, он из ЭТФ бывшего. Бывший человек из ЭТФ. Крис, я вам пересылаю QR-код Сашин.
Хорошо.
Так. Я думаю, что можно начинать более-менее.
Да.
Хорошо, давай.
Okay, so today's our speaker is Christofer Brav from Moscow Institute of Physics and Technology, Bondel's lab there. And he's going to talk, just quite forgot the exact title. Can you repeat it?
I also forgot the exact title, but it's something
I'm
like
going to reproduce it
let's say this.
Yeah, from the Poisson brackets and the string Lie algebra of a Calabi-Yau category.
Yeah. Okay.
Sounds interesting. Let us listen to the talk now.
Okay. So let me start with some motivation. I'll start with a nice construction of a symplectic manifold with a bunch of Hamiltonians on it, whose Poisson brackets can be computed due to Goldman. So the setting is in studying representations of the fundamental group of a surface. So let's fix sigma. This is a compact, let's say closed surface with, I'm going to fix the orientation, that's important. So I'll write the orientation as a class, as a fundamental class in the second homology of the surface. And I won't worry too much about the coefficients. So that exists integrally. But if we're doing representations with coefficients in a field, it's enough to take the orientation with coefficients in that field. And so associated to this data, we have the following. So there's the so-called character variety. There's one of these for every rank. So it parameterizes, so I look at representations of the fundamental group. I should fix the base point, but it doesn't matter too much because I'll consider everything up to conjugation anyway. And this should, if I'm studying the rank, say R version, should take values in some general linear group, let's say with complex coefficients. And I would consider these up to isomorphism. So these form the points of some algebraic variety. I'll write it like this. This is so-called character variety of rank R. And for, very simply, the reason this forms a variety, the reason it has an algebraic structure, is you can write down a presentation for the fundamental group with generators and relations. And then you're looking at inside the space of, some number of matrices. You're looking at those that satisfy these equations for the relations of the fundamental group. So that's a kind of concrete way to give it some kind of algebraic structure. By playing around with a functor of points, you can see that it's actually intrinsic. It's kind of independent of the presentation you choose. So this is the so-called character variety. And for sort of generic points, it's smooth. So we're going to focus on the generic locus. You can say exactly what you mean by that. So one genericity assumption you might assume is that the representation is simple. So it only has scalar endomorphisms. And for a point, so at a point, let me say it like this. So given a representation, I can associate to this a local system of vector spaces, a locally constant sheaf of vector spaces whose monodromy is this representation. There's a corresponding local system. This is kind of the easy form of a Riemann-Hilbert correspondence, where there are no singularities. So there's a corresponding local system. Let's call it E sub rho, whose monodromy, so rank R, whose monodromy is rho. So there's some standard correspondence between representations of the fundamental group and locally constant sheaves. And so I'm going to identify a point in the character variety with the corresponding local system. And one reason that's useful to do is that there's a natural identification of the tangent space in terms of this local system. So there's a natural isomorphism from, let's say, tangent space at rho to the character variety with the different ways to write it. Oh, what happened? No. So I can write it either as cohomology, first cohomology of the surface, with coefficients in endomorphisms of the local system. Or equivalently, this is an X group in the category of local systems from this local system to itself. In the case of a surface, say of genus 1 and up, the universal cover of the surface is contractible. So the surface, its homotopy type is completely determined by its fundamental group. And then if you want to compute these X, it doesn't matter whether you compute them in some kind of category of sheaves or you compute them in the category of representations of the fundamental group. So let's stick to that case for simplicity. Okay, so then
sorry, Chris, rho here is arbitrary or generic?
It turns out it's arbitrary.
Okay.
So this statement is true. If you make this, you consider the kind of character scheme, this will be the correct formula in general. What can happen at a non-generic point is that you have some singularity, so this dimension jumps. And then if you want to kind of control that singularity, it's better to consider the whole tangent complex at this point, and that will see the rest of the cohomology, so the other X groups. But for now, let's not worry about that too much. As I get deeper into the talk, I'll kind of introduce more and more structure of that sort. Okay, so there's this natural isomorphism, and if this is an unfamiliar situation to you, perhaps you're more familiar with moduli spaces of coherent sheaves, and then you have something very similar. If I have some moduli space of vector bundles or coherent sheaves on an algebraic variety, then the tangent space at a point corresponding to a given, say, vector bundle is the X group X1 from that bundle to itself, which is identified with first order deformations of the bundle. So that's the same, that's also the origin of this isomorphism. So in general, when you're studying some moduli space, the tangent space at a point corresponds to first order deformations of the kinds of objects that are parameterized by that moduli space.
Or what kind of model do you consider for the deformation? If you have sigma, what kind of model? Do you consider some kind of Dolgoprudnyi complex which computes these deformations or something else?
You could do this if you want. If you want to write down some explicit complex for the cohomology, you could turn the representation rho into not just a local system, but into a bundle with flat connection.
Yeah.
And then the local system is the sheaf of flat sections.
Yeah.
And yes, there will be a Dolgoprudnyi complex that computes this cohomology.
So I
in
just wonder,
fact,
but I thought it was the justification for this identification, and it's actually plays the role of.
So that identification only makes sense over, say, the real or complex numbers, where what I'm saying here actually will make sense over any field.
I see.
So you just have to interpret this as a moduli problem that parameterizes objects in an appropriate category. So you parameterize, say, complexes of sheaves with locally constant cohomology, and then these X groups are computed in that category.
I see.
And sorry, Chris, one more question. Can we extend this picture for non-smooth curves, sigma?
Yes. So in fact, everything that I've said is purely homotopical so far. So it would also make sense not just for a surface. I haven't used yet that it's a surface. So sigma could be like any homotopy type.
Okay.
So now I will show what more we can do with this. So what is good about having, say, a closed surface, this closed smooth surface with an orientation? What's special about that is that we have Poincare duality with local coefficients. So now, so let me use that. Okay, so there's a pairing. So I compare, let me drop M. there's a pairing of this cohomology with itself, which is the cup product pairing. So I can pair two H1s together, and then I can compose the two endomorphisms. And so I'll land up in H2 with coefficients in the endomorphisms. And then I can take a trace of that. I can take a trace of the endomorphism, so I'll get something in H2 with constant coefficients. And finally, I can cap against this orientation, this fundamental class, which gives an isomorphism with C. So altogether, I get some pairing from the tangent space with itself to the complex numbers, and Poincare duality with local coefficients implies that this is non-degenerate. It's also antisymmetric just because of the way signs work out for the cup product. So Poincare duality with local coefficients implies that this is a non-degenerate antisymmetric pairing. And I can do this for every row. So if you think about it carefully, you can see how to do this in families. So we have a symplectic form on every tangent space, but it actually varies naturally in the point across the moduli space. So the theorem of Goldman, I'll mention two theorems of William Goldman. I always forget how to spell Goldman, if it's 1N or 2. I think it's 2. So the theorem is that these pointwise pairings give a symplectic form on the whole well, strictly speaking, if I say it like this, it's on the generic part of this character variety. And so from this point of view, the difficult part of this theorem is showing that this antisymmetric 2 form, which pointwise is given as above, is de Rham closed. So that's the real content of the theorem from the point of view of Goldman. And so this is first just a construction of some symplectic moduli space. If you're more familiar with algebraic geometry, then this kind of, I don't know what you would call it, kind of study of topology via algebraic geometry. If you were studying moduli spaces of bundles, for instance, on a K3 surface, then Mukai around the same time showed something very similar, namely that again, there's a symplectic form on a moduli space of vector bundles on a K3 surface where it's given in the same way. It's some cup pairing followed by a trace, except now instead of Poincare duality, you have Serre duality. And the analog of the orientation is a trivialization of the canonical bundle on your K3 surface. So I'll come back to that again when I try to motivate what is a non-commutative Calabi-Yau. So why is this interesting? Perhaps this is most interesting because once you have this symplectic form, you can do some interesting kind of dynamics and kind of Hamiltonian mechanics on this moduli space. So Goldman observed the following. So there's a trace.
So that's true in generic point again, right? Not in.
Yeah. So later on, I can tell you how to treat the whole moduli space. But as I hinted at, to deal with the singularities, you need to understand the whole tangent complex.
Mhm.
You also need to understand automorphisms of objects. Basically, being non-generic means you have too many automorphisms.
Mhm.
And so the kind of best setting in which to deal with those things is, one, you have to consider a character stack. And two, you should consider a kind of derived version of the moduli space. And the advantage of doing that is that then the tangent complex has a nice expression in terms of the total cohomology of this local system. But for now, let's try to keep it kind of more classical and just put on some extra hypotheses in the local system to make the theorem true. Okay, so here's a construction of a bunch of functions.
So in this theorem, it's important that sigma is smooth or not?
It is, otherwise you wouldn't have, well, by smooth, what do you mean? Like, is the C infinity
Well,
structure important?
No,
or-
you said that we can replace sigma by a homotopy type. So for example, we can replace it by some singular curve, and then probably the moduli space
then
should be
it won't.
replaced.
So then it won't quite work because Poincare duality won't quite work. But there's a generalization that does work. So you could imagine, for instance, sometimes, so you're thinking in terms of algebraic geometry. You're like maybe a curve with a node on it.
Yeah.
And in topology, usually the way that's dealt with is by introducing some boundary. So this kind of singularity corresponds to some boundary component. So you could look at surfaces with boundary instead of closed surfaces. And then the relevant statement will be that the moduli space will be Poisson rather than symplectic.
The moduli space of what now?
Of local systems.
Okay.
Yeah, the same moduli space. It's just it will no longer quite be symplectic.
So
Because-
will be this moduli space a moduli space of flat sections again or not?
It'll be the exact same moduli space. It's the same moduli problem. All that changes is that the construction will now is a little bit more complicated. It will produce something Poisson rather than symplectic, and so it won't be given just by a pairing on a tangent space. And what's going on is that if you have a surface with boundary, you don't have Poincare duality, but you have so-called Lefschetz duality. It's a kind of duality for relative homology, relative to the boundary. So there is a generalization of this story. You could think of that as a kind of version for surfaces with singularities. If you actually took a nodal curve over the complex numbers as a, as a homotopy type, I haven't thought what to do in that example. I'd have to think about it, but there's probably some extra structure on the same moduli space.
Okay, thank you. And but in Goldman's theorem, we assume that sigma is smooth, right?
Yes, it's usually assumed to be closed or to be like smooth but with boundary.
Okay.
Mhm.
Thank you.
Okay. So here's a construction of a bunch of functions, a bunch of Hamiltonian functions. So given a curve, given a closed loop, and sigma, there's a function we may call it f sub alpha. It's a function from this moduli space of representations, this character variety to, well, affine line. Or if you just think of it pointwise, it's the complex numbers. So let me tell you what it is pointwise. So given a point rho, I want to tell you what its value, the value of this function is. So I choose a base point of alpha. So it lands somewhere in sigma. Once I do that, I can apply the representation to it. Now that, kind of involves different base points. However, that just gives me a matrix. And I take the trace of that matrix, it gives me a number. And once I take trace, I kind of lose the dependence on I wipe out the dependence on the base point because any two such things are conjugate for different base points. So there's a function like this. It's a kind of trace of monodromy map. And a convenient way to think of it as being, where is it defined? It's it actually only depends on the on the homotopy class of alpha as a free loop. So you can think of it as a map from the free loop space of sigma, so linear combinations of points in the free loop space, to functions on the character variety. Which takes loop alpha to this function f alpha. And now the right-hand side is actually a Poisson algebra because the moduli space is symplectic. And so you could ask how to compute Poisson brackets between these special functions which come from the topology of the surface.
Just before we proceed, may I ask a very stupid question?
Please.
Do you really need the assumption that you work with a surface? Wouldn't just a smooth manifold suffice, or even more general, some, I don't know, some CW complex?
So
Being
if I can always form the character variety
yeah,
for any homotopy type.
yes, definitely.
But in order for it to have a chance of being, say, symplectic or even Poisson, I need that homotopy type to, in some sense, be two-dimensional. And I'm going to discuss what happens in higher dimensions a little bit later.
Okay, I see.
So there will be some new, less classical additional structure on the moduli space that happens in higher dimensions.
So two-dimensional is the assumption you need to make it in symplectic, not some more general, not some high symplectic, something like that.
So in general, it will be what's called a shifted-symplectic space. But that's a very derived notion.
I see, yeah. It's
something that's kind of hard to see in classical terms. And the reason you see, and the reason you see that dimension 2 is important is, if I did tried to do the same construction in, I don't know, dimension 3, H1 would still pair with H1 to give something in H2, but I can't trace that out to a number.
Yeah, I understand.
What you can do in dimension 3 is you can pair H1 with H2 and get something in H3 and then take a trace.
Yeah.
So the natural pairing is not between the tangent space in itself, but between this tangent space and some other space. And this is the so-called shift in the shifted symplectic structure.
Yes, understand. Yeah. There's some generalization of the thanks. Yeah, quite what I thought it would be. Okay,
so Goldman found a very nice way to compute these Poisson brackets in terms of the topology of the loops. So you define the following. You define the so-called Goldman bracket of loops. Now, when I read it the second time, I begin to think it's 1n, not 2. So the Goldman bracket of alpha and beta, it's going to be something again in this homology of the free loop space. So there'll be some signs. I'll tell you what the sign is in a second. So I look at points in the intersection of alpha and beta, and for each intersection point, I can think of it as a base point along which I concatenate the two loops. So I start at beta, and I start at P in beta, go around beta, and then go around alpha, and that's my new loop. And here, epsilon P is the, what do you call it? Intersection number. So there's a signed intersection for where two loops cross each other on an oriented surface.
So do you assume that alpha and beta are in generic position? That is to say, they.
Yeah, I'm going to make a comment on that.
Mhm.
So in order for this formula to make sense, you need to perturb alpha and beta to intersect transversely in finitely many points. And then the formula makes sense as I wrote. And it's a kind of standard part of intersection theory on manifolds that you can do this, and that the answer will be independent of how you do the perturbation. So so anyway, if they intersect transversely, then this is the formula, and you can always perturb yourself into this situation. You can check that it's well defined, and moreover, you can check this actually a Lie bracket on this space of, well, H naught of free loops. So the second theorem of Goldman that I want to mention, maybe I should give them names like theorem A and theorem B, because I'll have analogs of them. Is that this map, which sends alpha to F alpha, is a map of Lie algebras. Meaning concretely that if I want to compute the Poisson bracket between F alpha and F beta, that's the same as computing this Goldman bracket of the two loops. That's something kind of more or less combinatorial. And then taking trace of action or trace of monodromy for that. Okay, so that's the second motivating theorem that I want to mention. And Goldman does these theorems appear in two papers of Goldman from probably mid-80s, maybe 84 or 85. And he does a lot of other interesting things in these papers. So he studies the flows that are determined by these Hamiltonians. You can study special configurations of these loops on the surface. So for instance, in genus G, there's standard 2G generators for the fundamental group. And you can choose G of them to be pairwise disjoint, so their intersections are empty. And then these Hamiltonians will commute. And so for a particular choice of rank, you'll have enough Hamiltonians to get some integrable system. Anyway, there's, if you go and look up the original papers and then you look at people who have cited this, you'll find a very large body of interesting work about the Hamiltonian dynamics of the system.
Sorry, does it have something to do with Hitchin system? It looks very, very similar.
It does under, so under the non-abelian Hodge correspondence, you can identify the kind of underlying space of this character variety with the total space of a certain Hitchin system. However, the complex structures are very different. And so it's not obvious how to kind of relate the Hamiltonian dynamics of the two, but there are some interesting conjectures now, theorems about so-called P equals W. So the cohomology of these two spaces will be the same, at least generically, because there's some topological isomorphism between them. But as complex manifolds, they're very different, and the cohomologies kind of come with different filtrations. And you can actually show that these filtrations of two that a priori ought to be very different actually match up. This is kind of a miracle. And I don't know, I don't know what the deeper explanation is for this.
So who are the authors of these theorems?
I don't know. I think there were a bunch of special cases. There were a bunch of special so I think the original conjecture or observation was due to maybe Tamas Hausel or maybe Migliorini, and then I think Davesh Malik and some of his students maybe have the strongest version of this to date. I'm not sure.
If you don't remember, don't worry, actually. Just
I don't know the story very well. I just know that those are the words you should say when someone asks a question like this.
Because actually they look very much similar, very similar to some construction of Hitchin, not quite the same, but very similar.
So actually when I give this talk, I have to make a choice about which examples to talk about. There's not time enough to talk about everything. And I could, in fact, give this talk from the point of view of the Hitchin system instead of from the Goldman system. But the Goldman system is kind of very elementary, so it's nice to talk about.
Yeah, I see.
Okay. If I have time at the end, I'll try to say something about Hitchin.
Can you take a link paper for this construction?
References for these two constructions?
Yeah.
So the papers of Goldman, let's see. Let me try to think what they're called. So it's two papers of Goldman from the 80s. And I think they're called something like Symplectic Nature of Moduli Space is one of them. And maybe the other one is called Hamiltonian Flows in Surface Group Representations. These are
Thanks.
These are two very nice papers. Okay. So now, given this, there are a bunch of natural questions you can ask. One of them's already come up, which is what would you do in higher dimensions? So that will explain. So I gave you some Lie algebra. People will call this the Goldman bracket. I also mentioned the string Lie algebra. So what is that? So Chas and Sullivan asked the same question that's already been raised. So what is the higher dimensional analog of the Goldman bracket? And I don't want to get into their construction. I want to actually give a different construction of the same thing. But let me tell you what the answer is. So their answer is that given is a closed oriented, let's say closed d-dimensional manifold. M with orientation. So it's always important to choose the orientation. There is they call it string bracket. So Goldman's bracket was defined to live on H0 of the free loop space. So here again, it will be the free loop space. But now you have to take into account higher homology. And because of the kind of shifts that appear in Poincare duality and other things, you need to shift it by 2 minus d. So here, if d equals 2, there's no shift, and this will just be in degree 0, it'll be this Goldman thing. So there's a string bracket on here, and here, actually, it's not on this, it's on the equivariant homology.
Great, sorry, why it's called string bracket?
Yeah, so I think the motivation for this is not extremely strong, but at the time there were some kind of papers where people were trying to study in string theory to study certain integrals on loop spaces. And the kind of algebraic structure that came out was kind of similar to some constructions in topological field theory. But I think the analogy is actually, if you think about it, not so very strong, so it might be a kind of misnomer. But anyway, this is what they call it. So this is, now the whole subject is called string topology. So it's the study of kind of extra structures on homologies of free loop spaces, where the free loop space is thought of as like a moduli space of some kind of strings in the sense of string theory inside of M. But I don't think you should take that too, I mean, I think the connection to string theory is, I don't know, it's kind of dubious. Okay, so this is, they have some kind of intersection theory style construction of this, but from the way they constructed it looks like it really depends maybe on a smooth structure on M. And in fact, it turns out to be purely homotopical. So there are other constructions of it, and I'll try to explain one today. And so I got interested in this whole story because I was asked the following question. So what is the analog? This is kind of 1/2. This is the analog of theorem A of Goldman telling you, no, this is the analog of theorem B saying, well, there's some Lie algebra, but you can't quite complete the theorem because what is the moduli space and kind of what is the corresponding Poisson algebra to which you should map? So what is the analog of the symplectic structure or Poisson structure, symplectic or Poisson? On this moduli space so that you can have an analog of theorem A in higher dimensions. And you can also have a full analog of theorem B so that this string Lie algebra is mapping to some kind of Poisson algebra on this moduli space, and the Lie algebra brackets match up. So in order to answer this question, I learned this question from Mahmoud Zinalian. So I'm grateful to him for drawing this to my attention some years ago. And it took me many years to kind of figure out a nice answer with Nick Rosenblum. So when I get to new theorems at the end, there'll be theorems with Nick Rosenblum. So this is the motivation. This is the motivating question that I want to solve. And the approach I'm going to take is that of actually a much more general question. So I need a digression on kind of non-commutative algebraic geometry. And people mean different things by this. So I'm going to do the kind of Bondol and Kontsevich style. So let me give a dictionary. So this is kind of usual commutative algebraic geometry. And this will be non-commutative algebraic geometry. And here I have, say, commutative algebras. These are kind of basic objects. And then you glue together from those, from their spectra, more global spaces in algebraic geometry. And the analog here will be just associative, but maybe differential graded associative algebras. And the reason for that, I'll say in a second. So if you glue together spectra of commutative algebras in an allowable way, you'll get schemes. And the analog here is going to be a differential graded category. So that's a category in which between any two objects, you have not just an abelian group, but actually a complex. And the way you get from one side to the other would be, for instance, you could take the derived category of quasi-coherent sheaves. So that would be a differential graded category that encodes a lot of the geometry of the scheme. Not everything, but a lot. And so what kinds of things are encoded by knowing just this differential graded category? You could look at so let me say for simplicity, let's say, let's fix a ground field of characteristic 0. Characteristic B is interesting, but much more subtle. So the beginning of the table works just fine, but now if I want cohomological invariance of schemes, for simplicity, I want to talk about it in characteristic 0. So I could look at the filtered, say Hodge filtered de Rham cohomology. I'll say schemes X. Hodge filtered de Rham cohomology. And it turns out there's a good non-commutative analog of this. So let me call the DG category C. There's a nice analog of this. There's a filtered kind of homology you can associate to this. This is called periodic cyclic homology. It also comes with the filtration.
What kind of filtration? Do you take?
So
Oh.
it's also called the non-commutative Hodge filtration. Is the question how to define it, or?
Yeah, more rather how you define it, because when you speak about the periodic cyclic homology of some algebra, I never heard about filtration. So
it's the filtration by powers of U.
So I mean this periodicity filtration.
Yes.
Okay.
But this actually people call this a non-commutative Hodge filtration, and actually for good reason. So if you want to go from one side to the other, there's a theorem that relates these two. So this is a kind of two periodization, and this two periodization is compatible with the filtrations. It takes one filtration to its two periodization. So this is the so-called Fagan-Siegen theorem.
Who's Siegen and who?
Fagan and Siegen.
Fagan-Siegen.
Mhm.
I mean
So
this
they-
original paper by Fagan and Siegen in 1980s.
There are
where
there are a few of them. So the paper I have in mind, it's called something like infinitesimal cohomology and periodic cyclic homology.
I understand.
So what they call infinitesimal cohomology is what I'm just calling algebraic de Rham cohomology.
I see. Oh, algebraic non-commutative de Rham.
Well, on the left, I have commutative de Rham, but in
On the
a
right,
kind of derived sense. And then on the right-hand side, I have periodic cyclic. And their theorem says that if you try to compute periodic cyclic for a commutative algebra, then the answer, naturally, is the two periodization of the usual de Rham cohomology.
Yeah. That's the variant of Hochschild-Kosten and Rosenberg theorem.
Yes, indeed.
I see.
And from my point of view, it's this filter version which is fundamental, and all the other versions will follow from that.
I see.
So indeed, I need to mention something about that. So what are the kind of individual pieces of the filtration telling you? So I want to interpret geometrically, say like Fp of H de Rham. So for simplicity, imagine it's smooth, otherwise I have to use the cotangent complex, and then it's still true what I'm going to write. So this will be R gamma X of, I'll have to put a shift in eventually. So let's see. So the part of the de Rham complex is greater than or equal to P. And I think I have to shift. Do I shift by P or down by P? Let me think just a sec. Yeah, no, it's just that without the shift. Okay, so I want to think of these as it's the complex of closed P forms. In the sense that, you know, if you look and say this was on a smooth affine, the stuff that appeared in degree P would be, the cocycles would exactly be P forms which are killed by the de Rham differential, so they're closed. And then on something that's not affine, well, maybe there's some higher cohomology, but the underlying complex is what I want to call the complex of closed P forms. And on the non-commutative side, well, there is this filtration. I haven't told you how to construct it, but the pieces of the filtration have a name. The pieces are called negative cyclic homology. And in degree P, now there probably is a shift. I have to think what it is, but it's not so important for me at the moment. So let me just say it's plus or minus P. So I want to think of these as kind of non-commutative closed P forms.
So does it have something to do with the non-commutative usual P forms in the usual sense? This universal.
No, because I'm just talking about categories, not algebras. And the thing you have in mind is not Morita invariant, and the thing I'm talking about is Morita invariant.
I see.
So by forcing myself to work in a Morita invariant way, I'm kind of forced to look at this thing instead of the thing you're talking about. But there's some kind of relation if you choose an equivalence between this category and modules over some DG algebra.
Mm.
They're not the same, but there's some maps between them. Okay. And finally, I could look not at, well, actually maybe two more pieces. 3 more for the whole dictionary of things that I need. So I could take the associated graded of the filtration. And we know what that is for de Rham. Just the usual thing. It's so again, if x is smooth, I just write it as omega p. P appeared in degree p, so there's a shift up by minus p. And what appears here is the so-called Hochschild homology. So maybe I should write that out. So this would be ger p of HP. It's the so-called Hochschild homology of C. And again, I should have thought this out in advance. It's either plus or minus P. I have to think about it. It's probably plus P. What's that?
Usual Hochschild homology.
Usual Hochschild homology.
Sorry?
Yeah, it's the usual Hochschild homology.
Oh, I see.
And so what this is telling you, so on the left-hand side here, the associated graded of the Hodge filtration is, this is Dolgoprudnyi homology, by definition. And so in this dictionary, I want to think of the associated graded of this non-commutative Hodge filtration. This is the Hochschild homology. I want to think of Hochschild homology as the Dolgoprudnyi cohomology of my non-commutative space. So in this dictionary, that's the correct way to think of Hochschild homology. And if you know the Hochschild-Constant-Rosenberg theorem, that's also exactly what it says. It gives some kind of isomorphism between stuff of this form and stuff of this form.
Mm-hmm.
Okay. And then one more thing we could do. So I have a filtered complex, some kind of de Rham homology. I have its filtered pieces, and I have the associated graded. But I could have also looked at the other kind of quotient. So I could look at the whole space modulo a piece of the filtration. So it could also, it's also sometimes in some calculation, you end up considering the following. And by the way, the Hodge filtration is defined just in terms of the kind of stupid filtration of the de Rham complex. This is what? It's R gamma x omega less than or equal to p minus 1. Yeah, that's what it is. And then over here, well, there's some analog. I could look at some HP modulo a piece of the filtration. So let's just do the F1 part. So the F1 part, I think, let me think. So I'll have HC minus. And I have to get the shift, right? So I think the F1 is this. So this will be, is this right? I should, let me not try to get it right now. So for one choice of the sign, this is the correct thing. So this is the so-called cyclic homology. So this is the kind of complete dictionary for all of the kind of variations on Hochschild and cyclic homology and where they come from in algebraic geometry. And they're all related by this, under this theorem of Fagan and Segan, or some version of the Hochschild-Constant-Rosenberg theorem. And finally, this is all cohomology.
I'm
all
sorry,
about-
just sorry for interruption again. I know that, of course, this is motivated by algebraic geometry on the left, but there is a well-known analog of the Hochschild-Constant-Rosenberg theorem for differentiable de Rham complex, of differentiable Hochschild complex, and which works for smooth manifolds, not for algebraic manifolds. So I wonder whether something like this exists in algebraic category, sorry, in smooth category.
Some kind of dictionary.
Well, left-hand side rather than the dictionary.
Yeah, right. So you know
I
what the
know
right-hand side is. So it's a reasonable question. I think there probably is a good answer, but I haven't thought it through carefully. So I can't produce it. I mean, so if I remember correctly, you end up having to look at things like differential operators on your smooth manifold to come up with a nice answer. But I don't remember how it works.
Yeah, okay. I mean, in some certain moment, the whole business of cyclic homology was somehow appropriated by people from algebraic geometry.
Right.
And just really lost the connection with this subject.
Yeah,
Okay.
I mean, Kohn, I think, was started out by thinking about.
Kohn is the opposite. Kohn is the opposite extremity. He only works with topological algebras and sister algebras.
Right.
The wild thing. So I prefer something in between.
but this dictionary right here, I mean, it's not spelled out in all detail, but it's implicit in this paper of Fagan and Segan.
Okay. I take a look. Thank you.
Okay. Okay. And finally, so this is all about differential forms. But speaking of manifolds, when you study differential forms, you also want to know about the Cartan calculus and how vector fields act on differential forms in various ways. So here you have vector fields. And I think of them as global sections of the tangent sheaf of X. So if X is smooth, it's just the tangent bundle. If X is not smooth, you should do some tangent complex version of this. And in degree 0, you know that there's a standard bracket of vector fields. They form a Lie algebra, but you could also do that at the chain level on the derived global sections of the tangent sheaf. So the answer will be well defined up to quasi-isomorphism if you kind of glue together the local brackets in some kind of clever homotopical way. So the non-commutative analog of this is the Hochschild cohomology. And there's a bit of a discrepancy in the degrees. So if you know the theory of Hochschild cohomology, there's the so-called Gerstenhaber bracket, which makes it into a degree algebra. So this is the Gerstenhaber DGLA on Hochschild cochains. And you have to shift it by 1 to make the Lie bracket of degree 0. And this has to do with the fact that the Hochschild cohomology actually has more structure than just that of a Lie algebra. And that the Lie bracket is a kind of something that you derive from this additional structure. So this is almost a complete dictionary. The other thing you have is a calculus, Cartan calculus and non-commutative calculus. And I won't go into detail about this, but there just as there's a way to act with vector fields and differential forms, so there's a way to act with Hochschild cochains on Hochschild chains, and in fact on all of these other gadgets associated.
I mean, Cartan calculus is differential vector fields, polyvector fields, they are contractions and Lie derivatives and so on, right? On the left. Sorry. Oh, Chris, do you hear me?
Сейчас это у всех случился или только у меня?
По-моему, это у всех случился.
Мгм.
Да, это у всех.
Мы вас слышим.
Не, к тому, что, по-моему, Крис выпал.
Крис
Да,
завис, да.
да. Все это очень интересно. Ты, Саша, понимаешь, почему я пригласил? Мне это очень интересно.
Я понимаю, да. Да нет, я же не против.
Не, я просто ты спрашивал. На какую тему? Вот ровно на ту, которая мне крайне интересна. Крис, я попробую Крису написать в Вичате и в этом, как называется, даже в Телеграме.
I don't know what happened, but Zoom froze for a minute. Do you hear me now?
Yes, we hear you now.
Okay.
Yes, I do.
Okay.
I do.
I don't know what happened.
Nobody does.
Nobody knows.
Okay. Okay. So I was saying that I won't go into
Cannot see
detail
your,
on this.
I cannot see your,
Cannot see the
no,
screen?
cannot see your slides.
Let me try again.
You could see your screen, but we couldn't see the slides, the notes you were making. I was just about to ask you a question about this Cartan calculus. So when you say Cartan calculus, is this the contractions, the Lie derivatives with vector and polyvector?
Yeah.
Right. Okay.
Yeah. So on the left is just the usual. You can take a vector field and contract it on a differential form, or apply the Lie derivative, and then the Cartan magic formula relates these two things with the
No.
de Rham differential.
Sorry, Chris, just one small question. Do you assume on the left-hand side that you consider just some schemes over the field of complex numbers or not?
It's not important, actually. So let's say we're in characteristic 0. The characteristic P is much more subtle if you're doing differential calculus. So in characteristic 0, let's say on a smooth affine scheme to begin with.
Okay.
And then on a smooth affine scheme, you just have vector fields. They're just, derivations of the ring of functions. And you can make them act by hand. You can write down formulas for how this acts on the de Rham complex by contraction or by Lie derivative and so on. And you can check that the Cartan magic formula holds. On a general scheme,
I mean to define the Lie derivative, we need some
no,
commodities.
you don't. So you don't actually. You can define it. So what is a vector field, algebra geometrically? You can think of it as an infinitesimal automorphism of your scheme. So infinitesimal means, you cross with spec of the dual numbers, and you take an automorphism of that, which is trivial on the central fiber.
So you mean you take a formal neighborhood, right?
I mean the following. So if this is my scheme, I can cross it with spec of the dual numbers. Viewed as a scheme over the dual numbers, so just the trivial deformation. And now I can look at an automorphism over this base. Plus, I could ask what it is on the central fiber when epsilon equals 0. And I can ask for that to be just identity. So this is what's called an infinitesimal automorphism.
Okay.
And you can check that these infinitesimal automorphisms are naturally in one-to-one correspondence with vector fields on X, sections of the tangent sheaf.
Okay.
So in this way, you can think of them as some kind of automorphisms. And then if you think carefully about what your de Rham homology theory is, you can check that these infinitesimal automorphisms act on it in a natural way. And you take that as the definition of the Lie derivative. And then you check with this definition, it satisfies the Cartan magic formula. And so if you happen to be over the complex numbers, it will agree with the usual Lie derivative, because that also satisfies,
It's clear. Yeah. I mean, this is a good explanation for students, because probably they just never heard about that. So, but X is arbitrary scheme, right? Not necessarily affine.
No, so affine is not so important. Smooth is convenient for simplicity. If you do this for a non-smooth scheme, then you run into some difficulties. So the de Rham homology isn't necessarily what you expect it is. The tangent sheaf is no longer a bundle, and so on. And you can fix all of these things, but you need to work with the tangent complex, the cotangent complex, the derived de Rham homology, and so on. So it can be done correctly, but for simplicity, just to understand the basic idea, you might as well imagine that it's a smooth scheme.
Okay. What is the main reference for this vocabulary? I suppose there is a review or something like that.
So Nick Rosenblum and I are writing a paper about the calculus.
What?
Nick Rosenblum and I are writing a paper about this dictionary. It took us a long time to kind of sort it all out. I think it's one of these things that's kind of understood to experts, but not really explained anywhere. So yeah, I'm afraid I don't have a good reference. We had to think about it for a long time to figure it out. So anyway,
can you paper serve as a reference or not?
So our paper should be done soon, although it's kind of never ending.
Okay.
So there will be a reference. The problem with our reference is that it might be in too much generality to be useful to normal people. But I hope that at least in introduction, we explain everything clearly in some basic examples. So I'm afraid the answer is no. There's not a good reference, and that we will provide some kind of reference, but it might not be good for some purposes.
Okay, it's a pity.
Yeah, it is a pity. It is a pity. So maybe at some point I'll have to write a review paper to kind of make it more accessible. So even for a smooth scheme that's not affine, there's something to be said if you want to do this at the chain level, right? If you want this to be a differential graded Lie algebra. So if you can, try, it's like inevitably to say this, you need to introduce a little bit of homotopy theory, because it's only defined up to quasi-isomorphism. So this is the basic, in the non-affine case, this is the basic problem. In the affine case, it's not such a big deal. It's kind of, if I tell you in detail what to check, anyone can do the exercise.
So it's not written anywhere, right?
I can give you some references probably for the affine case. For the smooth, yeah, so for the smooth case, I don't know. I mean, in the smooth affine case, I would say, I don't know where to point it to. I could just formulate it as a precise exercise. and it's not at all a hard exercise.
Мгм.
And then for the non-affine case, you have to know a little homotopy theory to even formulate the problem. And in the singular affine case, I guess I could also provide some kind of reference for what this DGLA is. It's called the Harrison complex is a model for it, I think.
Мгм.
Anyway,
Okay.
I can try to provide some kind of pointers, and we can talk about it
Okay.
more another time.
Okay.
Okay, let's go on.
Okay, so this is the dictionary I want to work with. And the reason I want this dictionary is it was important in these constructions of Goldman and also Chas-Sullivan that we were working with some oriented manifolds. Actually, the fact there were manifolds was not so very important, but the fact that they had this fundamental class was very important for the duality. And so what is there's an algebro-geometric analog of this. And let me say that before I do the fully non-commutative version. So what is a Calabi-Yau manifold? So a Calabi-Yau, let's say, variety of dimension D. Let's say it's smooth for simplicity. There's something you can say even if it's not smooth. So a Calabi-Yau variety of dimension D is, well, it's a variety of dimension D, say a smooth variety. Let's call it X, plus, this is part of the structure. So I think of Calabi-Yau not as a property, but as a structure. So if I think over the complex numbers, it's the holomorphic analog of an oriented manifold. And if I were talking about smooth manifolds, an orientation would be a nowhere vanishing top differential form. So here I look for a holomorphic volume form. So this will be a section of the top holomorphic differentials, if I'm over the complex numbers, otherwise just algebraic, which is nowhere vanishing. Alternatively, you could think of that as a section. It's a map from the structure sheaf into the sheaf of differentials, which is an isomorphism. So that's how it's usually thought of. And in complex analysis, you think of this as holomorphic analog of an orientation or of the volume form. And I would like to rephrase this in terms of this Hodge filtration on de Rham homology, which appeared over here on the left-hand side. So remember I said that the Hodge filtration was seeing this natural filtration of the de Rham complex. But in dimension D, when P equals D, this will be at the very top and there's nothing beyond it. So alternatively, I think of D, think of theta as living where? I want to think of it as living in the top, well, I guess bottom, it's descending filtration. The bottom of the Hodge filtration, I need to shift this, it looks like, by D to put it into degree 0. So what is this? This is R gamma X omega D. I think of theta as defining a degree 0 element of this complex. And the reason I want to think of it like that is then that will admit a non-commutative generalization. So let me give a definition now. It's a kind of quasi-definition because there's some technical point that I don't want to go into. So, so given a nice DG category C, we say a Calabi-Yau structure of dimension D, or it's a, if you like, a non-commutative volume form. This is, it's a class theta in this dth part of the non-commutative Hodge filtration on the periodic cyclic homology, which, as I said, this is right. So I know what the answer is supposed to be here in terms of degrees, and so that will fix those degrees that I was uncertain of before. So this is supposed to be a degree minus D. Right. Which means that, okay, let me finish this and I'll go back and fix the degrees, and then I can send you notes at the end. So it's a class like this, satisfying a non-degeneracy condition. So I need to say, in what sense is this a non-commutative volume form that is nowhere vanishing? And I'll just say what it is. So you can phrase it in terms of the following. So there's a map from this piece of the filtration down to the associated graded. Because the associated graded by definition is a quotient of one piece of the filtration by the next piece of the filtration. And so I'll look at theta first as living in some layer of the filtration, and then second as its image in the associated graded. I won't distinguish notationally between those. And then I can look at, as I said, there's this non-commutative calculus. So I can look at this Gerson-Haber-Lie algebra, and I can contract it against this theta. And this theta lived yeah, I probably want to do it without the shift. There would be an induced map like this. And I asked that it be a quasi-isomorphism. This is my non-degeneracy condition. And you can check that under this above dictionary, that every smooth Calabi-Yau variety in the usual sense, given by a volume form like this, will naturally induce this structure because the class here will give rise to the appropriate class there, and the non-degeneracy will match up. And in fact, the Calabi-Yau structures in the non-commutative sense for applied to an object coming from actually commutative geometry will be exactly the usual Calabi-Yau varieties. There's no exotic Calabi-Yau structures on a commutative variety. However, there are purely non-commutative examples of this. This is what makes the theory interesting. So let me give you a few examples of this, why I'm introducing this. Are people still there, or have I lost you again? I'm afraid I lost you again.
No, we can hear you.
No? Okay, very good.
No, we can hear you.
Okay. Okay. I'm afraid of just talking to myself for 5 minutes, 10 minutes, and not
No,
knowing. Okay.
Ground for one time.
Okay, so I'm motivating this definition in terms of the usual notion of Calabi-Yau variety from algebraic geometry. I abstract this under this dictionary to non-commutative geometry. But in order to justify this, I should show you some examples that are really kind of different from what comes from algebraic geometry and yet fit into this framework. And so this allows us to kind of move ideas between algebraic geometry and, say, topology or representation theory via this idea of non-commutative algebraic geometry. So the first example actually is this one I was already talking about from manifolds. So suppose M is a closed manifold with orientation of degree D. So this is topology. For instance, a surface, closed oriented surface. Then I claim that if I take as the differential graded category, I take the category of local systems on M. So you can understand that. So for simplicity, if M is an Eilenberg-MacLane space, it only has pi 1 and no higher homotopy groups, then you can just take this to be category of representations of the fundamental group. In general, it's some kind of homotopical analog of that. So one way to say it is, you look at all complexes of sheaves on your manifold, say sheaves of vector spaces, and you look at the subcategory of those that have locally constant cohomology sheaves. So then the claim is that this has a natural Calabi-Yau structure of dimension D.
Sorry, just didn't quite understand it. I thought that the definition of local systems was the representation of fundamental group, but now you say it's something different.
It's the difference between, it's about getting the derived category correct.
Okay.
So suppose, for instance, that M is simply connected.
Okay.
Then there are no interesting representations of the fundamental group. They're all trivial.
Sure.
Does that mean that the category of local systems should just be thought of as the category of vector spaces?
Maybe not.
Well, maybe not, because you would like, for instance, that the X groups between the trivial representation, the trivial local system itself should see the cohomology of the manifold.
Okay.
And so if you want that, you should think of local systems as locally constant sheaves, and then you should compute those X in some ambient category of all sheaves.
Uh-huh. So
So
like
only
this.
so it's only when the manifold is an Eilenberg-MacLane space that you can say everything purely algebraically in terms of the fundamental group.
Mm-hmm. Because there's also for me these sheaves and well, I don't like sheaves, but would it be correct to say that we just work with lead bundles?
Yeah, you could say it like that. So you
So
could
they
work
could
with
be-
flat bundles, and then you could compute these X in terms of a de Rham complex for those flat
Yeah,
for the
that's what I meant.
homomorphisms. Yeah, so you can do that.
Okay.
So that will give the same category I'm talking about if you do this with real or complex coefficients.
Yeah, because of course there are more flat bundles than there are representations of the fundamental group, because you actually to get the representation you actually need the connection, and the connection is something is in extra, some extra.
Well, what do you mean by flat bundle? I meant bundle together with flat connection.
Oh yeah, okay. That's more or less what I meant. Yeah, because actually flat bundle is bundle plus connection, it's not just bundle. I mean, it's so
Yeah, that's right. Yeah. So I meant bundle plus connection, and then that is the same data as you know, up to equivalence. That's the same data. So the objects up to isomorphism will be the same as representations of fundamental groups. But if I want to get the correct X groups between them, I either need to compute it in terms of the de Rham complex, or embed this into some bigger category of all sheaves. But it's not enough to just study the homological algebra of the fundamental group, is my point.
Yeah, sure. Because fundamental group, everything is equivalent to the presentation, but it's not just the equivalence is non-trivial information. Yeah, sure. Okay.
Okay. So I can try to explain this a little bit, or give an example from representation theory. How much time do I have?
Well, actually, 15 minutes, I would say, because we studied it later.
Okay. So let me I want to state a theorem. So let me mention one more example, state my theorem, and then we'll see how much time I have left. So the next example is Q is a quiver, say finite. And then I have the double quiver, where for each arrow, I introduce an arrow going in the opposite direction. So if I have an arrow A, I introduce a dual arrow A star. And I do that for every arrow. And then I can consider the path algebra of that doubled quiver. And there's a special element in there. What is the best way to do this? So I can look at one copy of a polynomial algebra for each vertex. And the special element is it's called the pre-projective element. It's a kind of non-commutative, it's related to some non-commutative moment map. So what this is, if I think of this as this as a unit, so where does the unit go? It goes to the sum over all arrows of the commutators and the duals. So this is sum over arrows in the original quiver. There's some special element in here. And then I can also consider, I can choose hold on, let me think. I have to think if what I want to put here. I think I just want to put K. So at each vertex, I can assign a scalar. And I want to consider the push out. So what am I doing? I'm imposing some relations. I'm saying that this pre-projective element should actually become equal at each vertex to some scalar. So the result is, it has a name, it's called the deformed pre-projective algebra. It is the doubled path algebra modulo relation that this pre-projective element at each vertex becomes equal to some specific scalar. And the claim, and this maybe really does take too much time to explain, is that this deformed pre-projective algebra has a 2 Calabi-Yau structure.
So sorry, just I think I missed what is Q0 in this left upper left corner.
That's the vertices, and then this would be the arrows. So
Vertices-
Q0 is vertices and Q1 is arrows.
Yes, sorry. Okay, yeah, I see.
Okay, so this has a 2 Calabi-Yau structure, and you think of it as a kind of non-commutative oriented surface. And if you are familiar with the story about pre-projective and deformed pre-projective algebras, there are also multiplicative versions. This is kind of the additive version. And in fact, the group algebras, fundamental groups of surfaces, are examples of multiplicative pre-projective algebras. So you could think of this as an additive version of the group algebra for a fundamental group of some non-commutative surface. Okay, so these are kind of two other motivating examples. I have those that come from algebraic geometry, those that come from topology, and those that come from representation theory. And now the theorem, I'll have to start it a little vaguely, and then I can give more detail than you want to hear. This is a theorem with Nick Rosenblum. So let C, comma theta be a Calabi-Yau category of dimension D. So theta is this Calabi-Yau constructor. Then the group of exact Calabi-Yau automorphisms. So I could look at automorphisms of C that preserve theta, but in some exact way. Let me call it aught C, comma theta x. Has a Lie algebra, has a DG Lie algebra. This is actually some kind of derived algebraic group. This has a DG Lie algebra, whose underlying complex is the cyclic homology of the category shifted by 2 minus d. So you can see d equals 2 is something special. And the hard part of the theorem, it's actually be two different theorems in the papers. And there's a Hamiltonian action of this Lie algebra on, it's called the moduli space of objects in C. So if you imagine that C is some kind of like non-commutative local systems, this is a moduli space of local systems. There's a non-commutative version of this character variety that Goldman studied. Or say the moduli space of bundles that Mukai studied on a K3 surface. So Hamiltonian means that you also using theta, you can put some kind of symplectic form on this moduli space. It's actually a shifted symplectic form. And not only do these vector fields preserve that symplectic form, they actually give some kind of Hamiltonian vector fields preserving that symplectic form. So this is stated like this. This is the analog of both theorem A and theorem B of Goldman. Actually, part of what motivated this was with another collaborator, Toby Diekerhoff, we first found the analog of theorem A. And then Nick Rosenblum and I wanted to do the analog of theorem B, but in the process, we had to rework this version of theorem A. So this is, you should think of this as that full, all-dimensional, non-commutative analog of these theorems of Goldman. And if you apply it in the given examples, you recover either the Goldman bracket or the string bracket of Chas-Sullivan if the category C is local systems on a higher dimensional manifold. If you apply it to this deformed pre-projective algebra, you'll get what's called the necklace Lie algebra. So they're very, you can also apply it to the Hitchens system. So you kind of see why Hitchens Hamiltonians should commute from this point of view. Not just a proof, but like an explanation why they're coming from actually an abelian group acting. So anyway, that's the theorem is supposed to
Important.
the theorem is supposed to kind of bring together all of these different examples as the same phenomenon.
Mhm. Mhm. Yeah. So
Okay, so
just
What is
anything
known
else?
about this moduli space of objects?
so it's very big because we're privatizing all the objects in the category, or all small enough objects. You can study things like what are its connected components, right? It's like when you study the Hilbert scheme, you fix a Hilbert polynomial and you get a particular connected component of the Hilbert scheme. We know the tangent complex at a point. It's expressed in terms of some X groups from the object to itself. That was already known. It's known that the moduli space is algebraic in a certain sense. They're kind of charts that you can cover it with. It's an Artin stack in a certain sense.
So it's a stack, right? Not a scheme.
Yeah, that's right. Yeah, and in fact, it's like it's a higher derived Artin stack. This is what it is. And so to extract from this theorem some kind of more down-to-earth application, in your given example, there's always some extra work to do. So you need to kind of isolate the piece of the moduli space you really care about for some application. And then you typically need to rigidify the problem a little bit in order to kind of kill some automorphisms so that you're not dealing with a stack, and so on. So in practice, this is kind of a template. And then in an application, you have to do some extra work to extract from it something useful.
So stack is in the sense that it's kind of sheaf of categories, right? Something like that.
So I think the best way to think of a stack is the way homotopy theorists think of it. So what is from the point of view of functor of points? What is a scheme? You know, it's some kind of special functor from rings to sets.
Yeah.
And that works fine if the kinds of things you're trying to parameterize have no automorphisms. If they have automorphisms, you should say, right, it's a functor from rings to groupoids, where the morphisms in the groupoid are all invertible, they record some automorphisms or isomorphisms between different objects. And you can think of a groupoid as defining a homotopy type which has only pi 0 and pi 1. The pi 0 is the kind of isomorphism class of objects, and the pi 1 is automorphisms of any fixed object.
Yeah.
And so this turns out to be a useful way to think of stacks, because what you can study are kind of sheaves of homotopy types that maybe have higher homotopy groups.
Mm-hmm.
And this is a more
never seen a well-defined definition of stack. I mean, every author gives his or her own definition, and sometimes it's difficult to go from one definition to another.
So the I mean, if you look at the old sources, like Giro wrote about this, then I think there's a kind of horizontal way and a vertical way to think of it. And then to go between them, there's something called the Grothendieck construction. So you
I always thought that sheaves are some kind of, no, sorry, that stacks are some kind of sheaves of categories. And of course, when you go from on the intersections, you need to fix some natural transformation from one to another. And also you need to, in between these natural transformations, you need to introduce further natural transformations on triple intersections, so on and so forth. And that's more or less what I imagine a stack should be. But that's naive.
Yeah, but if you say it like, I mean, that's all correct. You can say things like that, but then you can get lost in the combinatorics of the definition if you get too explicit about it. So it's actually the same problem that you run into with this thing, this R gamma. So if you want to talk about the Lie bracket of vector fields at the chain level, what do? You should cover X with, say, affine charts, and then, you have some complex that computes this R gamma. How do you define the Lie bracket on it? So you'll end up with similar kind of considerations about the double and triple and quadruple intersections and so on. So you need some kind of machine for handling this in a way that you don't go crazy.
Well, in just globalization, you can actually use some kind of standard simplicial machinery to globalize these naive ideas. I think it should work.
Yeah.
Does it?
Yeah, so it does. I mean, there's something called there's a model category of simplicial sheaves. That's one way to do it.
Okay, so I see now. Okay, so you're going to publish this soon. Well, it's already been published.
I don't know if, well, it's going to be on the archive soon. I don't know about published.
In the archive. On the archive.
Yeah.
Okay.
Yeah.
I mean,
yeah, so it's just a matter of at this point, it's a matter of sitting down and finishing writing. I mean, it's all worked out in detail in our notebooks. Yeah.
Because for me, the most intriguing part is the missing middle. I mean, there is this pure algebraic construction where you work with sheaves, schemes, and so on and so forth. There's this very abstract and very topological constructions of Kohn, where he works with C-star algebras, von Neumann algebras, and all types of topological algebras to obtain some non-commutative geometry in his sense. But what is really missing, in my opinion, is this golden middle, which was used like some in the beginning of the 80s by people from Belgian school who proved the first version of deformation quantization program using this using this Cauchy and cyclic homology for algebras of smooth functions, but just when they just had to limit the complexes to differential operators and so on. So I really wonder whether there is have there been any attempts to fill in this gap somehow by any person, because I see that there is this wide gap between these two extremities. And
I mean, I think there are people who do understand it all. I'm just not one of them, but Tsigan probably is able to.
Yeah. Yeah, maybe. Okay, yeah.
Chris, maybe just one last question. Could you deduce some concrete examples of Hamiltonians, say, using this technique?
Yes. Yeah. So this example with the quivers is actually very explicit, and was in some sense already known. So you can look at a paper. You can look at notes of Ettingolf on the Closure-Moser system. So you might like this.
Yeah.
So he explains there what this looks like for the case of it's one vertex and a bunch of loops.
Mm-hmm.
So if you apply this story to that example, then for a particular choice of, so what do you have to do? You have to consider a moduli space of representations of this algebra. And then you have to work out what this Lie algebra is. So this Lie algebra is what's called the necklace Lie algebra. It's something very explicit. You write down a basis, you have a formula for the bracket. Then you have to look at a moduli space of representations of a particular dimension. If you choose the dimension right, and you choose the elements of the Lie algebra right, then you get exactly the additive Closure-Moser system.
Mm-hmm.
Another person who studied things from this point of view is Maxime Ferron. And maybe, I think he was a student of Charles.
Mm-hmm.
So they have more exotic examples of integrable systems that come have this kind of quiver description. So not just the usual additive Closure-Moser, but maybe some multiplicative versions, maybe some spin versions, and so on.
Yes, but it seems to me that they got these examples by another technique.
My point is that the all of these examples, the Goldman examples, these quiver examples, the Hitchin example, and so on, they're actually all examples of the same type. And so you could ask, well, who cares? What is this good for? I would say it gives a kind of recipe for looking for new examples. It gives a kind of paradigm. So that I have techniques for producing these Calabi-Yau structures. That's another story. How do you produce these non-commutative volume forms? And so there's just like you can glue together surfaces with boundary to get closed surfaces by cobordism. There's a kind of non-commutative analog of this that I studied with Toby Dekerhoff. So there's ways to put together simpler non-commutative pieces into more complicated things and build Calabi-Yau structures in this way. So once you do that, once you produce your Calabi-Yau category, then you need to compute this Lie algebra somehow. That's not always easy. And then you need to see if there are enough commuting Hamiltonians in it to maybe get some integrable system. So I have some ideas about examples to look at, but we don't yet have genuinely new examples. As I was saying, it's kind of a paradigm where you have to do further work to apply it to some particular example. So for instance, I have some, you could ask, how can you do elliptic Closure-Moser in these terms?
Yes, for example. And as far as I remember, not all deformations of Closure-Moser systems obtained by pupils of Charles and Veselov could be obtained via the representation theory.
Oh, that's interesting. That's interesting. I would like to see that because in general, a category of modules can emit more deformations than the underlying algebra does. So this is something very common in algebraic geometry where you could start with, for instance, a K3 surface. And you could look at it, say, the category of coherent sheaves on it. And if you deform the variety, you'll get a deformation of its category of sheaves. But there are deformations of this category of sheaves to something totally non-commutative. They don't come from any commutative K3 surface. So it might be, if you have a reference, I'd like to see it. It might be this kind of phenomenon where there's some kind of deformations that can be seen at the level of the category that can't be seen at the level of the initial data.
Well,
Yeah,
there are
interesting.
many examples produced by the school of Vesel, of so-called deformed Calabi-Yau systems.
Okay. Okay.
And some of them could be obtained via representation methods by Etinghoff, but not all of them.
Okay.
Like you can just
So
look at them.
deformed
But they are
Calabi-Yau.
quite concrete. They're quite concrete. I mean,
Okay. Okay.
yeah.
Okay. That would be interesting to look at.
Really hard to go
Because
from.
because actually our theorem, I mean, I didn't say how to prove this, so I phrased it in terms of automorphisms, because I think from the point of view of Hamiltonians, that's the most natural thing. But you can also view this in terms of deformations. There's a kind of, in deformation theory, a way to go back and forth between automorphisms and deformations. And in those terms, you're studying certain deformations of this pair, of the category together with this volume form on it in a compatible way.
Okay.
And this DGLA is exactly what controls this deformation problem.
Okay, that's all very interesting. It really deserves, I think, a separate lecture. I mean,
Yeah, I
the
think so.
deformation procedure is one of the main topics studied at this seminar. So if you feel like you are able to make another talk on this next time, then we'll be very glad to.
Well, probably I need a little break, but
Yeah, sure.
Yeah.
Don't worry about this. If you would like to, we would be glad to hear.
Yeah, let's do it another time. I'll look at the calendar.
Definitely. Okay, thank you very much. It was a very interesting talk. Can you please send
thank you.
the slides?
Yeah, I'll fix the shifts and then send you the slides.
Okay, thank you. And also, yes. So next time we'll have a break because of some events in the Moscow State University, but then in 2 weeks we'll meet again. I'll send the invitations in appropriate time. Okay, thank you everybody for attending the talk.
Okay.
All right, thank you. Goodbye.
Thank you. Bye.
Bye.